And quiet down, please. All right, so the first speaker back up from lunch is Andrew Young, who's making his way up to the front. You're coming. All right, so one word of note, our presenter is not functioning, so just
okay.
Hit enter.
Easy enough.
Take it away.
Hey everybody, my name's Andrew Young. I'm at Sandia National Labs, and I'm going to give sort of a general overview of this Astra machine, which is a petascale ARM platform for the DOE's ASC supercomputing effort. Feel free, by the way, we can make this interactive. Hopefully, I know it's right after lunch, so hopefully nobody will go to sleep. But if you want to ask any questions, feel free to just stop me or shout or something like that. So to give you a brief overview of what you should expect for the next, I don't know, 25 minutes or so, first we're just going to review or talk about Vanguard and what we mean by the Vanguard program and in the context of prototypes. And then, of course, we'll dive into Astra, which is the petascale ARM platform that we're putting together as we speak. I'll also dive a little bit into an area of interest for me, especially, which is the ATSI, or Advanced Tri-Lab Software Environment, as well as some of the R&D activities that we're envisioning and spinning up right now for this project. So first, Vanguard. What is Vanguard? The point of Vanguard is really to prove the viability for sort of emerging and advanced technologies for impact with our integrated codes, our production codes, and doing so at a significant enough scale. So really what we can do here is try to expand some of the HPC ecosystem a little bit and really look at proving out what is potentially, currently unproven technologies. With this gives us some opportunities to potentially take on slightly higher risks than we normally would with, say, a production machine procurement to really try to speed up technology advancement and lower the risk to the actual production codes when, say, a usable machine hits the floor. So this is sort of interesting. It's a new approach. And we really are trying to focus this program on addressing not only hardware, but also software challenges that we see within the HPC ecosystem. So why does this matter to anybody here? Well, phase one of this Vanguard program is focused on expanding the ARM ecosystem. So to give you, there we go. To give you a little more sort of where does Vanguard fit in, it's sort of an interesting middle point, where on one side we have test beds, which everybody's familiar with test beds on the order of several to several hundred nodes, whereby you can, we usually cover a breadth of architectures, trying to, stay up to date on the latest and greatest of whatever's happening. But this really requires brave users, and our, system administrators will also adamantly say it takes brave administration as well for these machines. But there's only so many things that you can really sort of address at the testbed scale. And it's usually a large jump to actual production machines. And within the DOE, this is generally ATS or CTS based platforms, which really are, the big sort of news articles that you hear through DOE with the large leadership class machines focusing hopefully soon here on exascale. And oftentimes they also do represent advanced technologies and sort of a first of a kind of a new architecture, which, but are also targeted for production use. And you can see how this is at times, sometimes, potentially conflicting. So Vanguard's in the center, and the idea here is we can build a system that's big enough to attract users, but do more than just sort of dabbling. We can actually start to use this, if things go right, for production cycles. And it also allows us to have an R&D effort surrounding this activity to sort of fill the gaps whenever necessary. So Sandia has been looking at ARM platforms longer than I've been at Sandia. We've got a long history dating back to some of the original XGene systems, and then transitioning through to the ThunderX series CPUs. Currently, today, we're right on this line where we've been using this system that we call Meyer, which is essentially part of HPE's Comanche test platform. And we're right at the verge where Vanguard and Astra is starting to arrive today. So we've been looking at ARM for a while, and we thought this was the right point in time to sort of intersect and dive in and find some nice advancements. So what is Astra? Astra is a what we expect to be the first sort of petascale ARM platform. It's 2.3 petaflops peak, but that's really not the interesting point, and probably most people in the room know this. We are really excited about, the 885 terabytes of peak memory bandwidth. And this is at a size that's large enough that we can, with, roughly a third of a petabyte of main memory, we can look at really interesting problems with that sort of scale. And really here, what we're really, again, focusing in on is demonstrating that this sort of architecture is viable for our supercomputing needs. So let's take a look a little bit at the actual architecture of Astra. So as a base, we have a HPE Apollo 70 node, which is based with a dual socket Cavium ThunderX 2 CPU. This is the 28 core version that we decided on. And probably the most interesting thing, other than obviously it's ARM and its general availability at this point, is the 8 sort of DDR4 controllers per socket. So unsurprisingly, this also has a fairly fast interconnect using InfiniBand's ConnectX-5 InfiniBand card, and we will be running the TriLab operating system stack, which is very analogous to Red Hat, so for at least external purposes. So this is the general sort of overview, and again here we really see that we've got 8 DDR4 channels per socket, which is really interesting, and we're also using Mellanox's Socket Direct to have dual 8x links to each socket to really be able to fully drive that memory bandwidth potentially through fast message passing. There's of course a management network which connects via just a Ethernet 1 gigabits link. So from this individual node design, we then have 4 nodes per Apollo 70 chassis. That chassis then gets assembled into a rack, which is, 18 of these are put into a rack along with 3 sort of L1 IB switches. And then in total, the system is made up of 36 compute racks, or 9 scalable units in this case. So as well as the 3 director class IB switches. So it's a pretty significant architecture, and of course, with any sort of machine, it's more than just pure compute. You actually need a lot of other services to go along with this. So we have several login nodes. We have planned for 3 LNet Lustre routers for connecting to the external storage system at Sandia, and several, just a couple of general service nodes. As I mentioned, the interconnect is EDR InfiniBand. This is 2-to-1 overscribed, and it's pretty typical for an InfiniBand deployment at this point. We're using HPE's cluster manager, the HPCM, to be able to boot over the network. And the other interesting thing is we have all flash-based platform storage as well. So not incredibly large at 400 terabytes, but large enough that we can actually, again, focus on being able to do initial production runs on this. So from a network standpoint, again, this should be pretty, I would say, standard to most people who are InfiniBand, or who are familiar with the InfiniBand architecture. But it's between L1 and L2, it's a 2-to-1 oversubscription, and then the director class switches are fully subscribed. So when you add it all up, you can actually count that that's around 2,500 or just under 2,600 compute nodes, or just under 150,000 cores. So this is a large enough system that we can really start to do some interesting things with. Sort of a novel thing for Sandia as well is where we're actually putting this machine is a new sort of data center and machine room. Using these interesting thing called thermosiphons. I don't know if anybody's heard of these before or familiar with them, but they're rather interesting. And the idea here is that we're going to run this machine room without chilled or without compressors year round. Most of throughout the year we'll be able to run directly with a thermosiphon, which will move a lot of the excess heat in a water loop, and then only during the really hot sort of months out of the year, we can use evaporative cooling. So not only is this a fairly efficient design, it also is one in which saves millions of gallons of water a year, which in the New Mexico desert is actually really important. So there's a link there to a partnership that originally developed some of this initial thermosiphon work with partners at NREL. So why ARM? Why ARM64? Why Cavium? Well, as I sort of alluded to earlier, one of the nice, or really, first-class problems we see is regarding memory bandwidth, and we see really good numbers for the 8 DDR4 controllers over what we can currently find, say, with Intel Skylake. So this is really exciting. This is one of the nice drivers for what we're starting to really look at and care about in this machine architecture. Yeah, you're right. This isn't working. We also, so far, have seen really good interconnect performance using the Mellanox ConnectX-5 cards, being able to drive what essentially we're expecting to be our, what is fully expected bandwidth, as well as over 75 million messages a second. So our message rates are also pretty high. This took a lot of sort of getting right with socket direct, but once you're there, we're seeing the performance that we were expecting. And this is actually really exciting. And it goes to show that these sort of architectures are more than just vendor locked into Intel or the x86 system. So. Specific to Sandia, we have the mini apps, and we're seeing several really sort of key first indicators here for leveraging the ThunderX2, seeing notable performance improvements over Haswell-based Intel x86 architectures. And again, a lot of this goes back to having the 8 DDR4 memory controllers as well. But we think there's further optimization as we start moving forward here too. There's certain examples here that we're finding that we think further improvement in the software stack will continue to yield good results. So that's a quick and dirty overview of sort of Astra and the machine that we're plunking down literally today. I think the next shipment is due rather soon, although Andy will probably talk more about this. So now I'm going to dive a little bit into ATSI, the Advanced Tri-Lab Software Environment. And like I said, Vanguard is meant to be more than just initial hardware evaluation. Many people know that here have focused extensively on some of the topics in which we'll talk about as part of ATSI, but really what we're trying to do with ATSI is start to put all that stuff together and accelerate from a software standpoint the ARM ecosystem for our mission computing needs. So, and again, a lot of this revolves around ensuring and proving out that we're going to be able to get the performance results that we're expecting out of this architecture. It's one thing to say, all right, I can do this at small scale. It's another thing entirely to be able to have a software stack that developers can rely on and have it be similar to what they've worked with in the past, and also to be able to get the performance in which they're expecting. And so again, this is a full sort of top to bottom stack. So we're going to be looking at the programming environment with the compilers, math libraries, OpenMPI and other MPI optimizations, as well as, sort of interesting opportunities that we're seeing with an operating system standpoint. And I'll talk a little bit more about that in a minute, as well as, ensuring that we can do the proper job scheduling that you'd expect through Slurm in our case, and manage the system appropriately. So it's a full system view rather than, a very quick, cobbled together set of tools that maybe you'd find when evaluating, a testbed infrastructure. So really, at the end of the day, we're trying to make the software ready and hopefully hardened by the time it goes into production use. So as I mentioned, we have the software stack that we're putting together, and we've focused on a couple of key components, including making sure that this is an open environment. We're extending tools whenever possible, and we're taking inspiration not only from our developers directly, but also existing community efforts, while still enabling and designing a situation in which vendors or anybody else can add and contribute to this when and where necessary. And I think that's a really key aspect as well. We're also in this effort prototyping new environments that aren't really common, from a software standpoint at least, on supercomputing systems today, to be able to support new machine learning or data analytics workloads that we're seeing gaining in prevalence quickly. So like I mentioned, we're leveraging several existing efforts. We're building on the TOS operating system, and we're extending the Open HPC model when and where appropriate and possible, as well as leveraging several other experimental system software aspects. So we originally started by just trying to come together last year about what's the idea, what do we really need to do from the ARM perspective, and we've now slowly iterated through that through various initial design documents, and now have a working sort of software stack that we've put together on this HPE Comanche testbed, but this will be the first programming environment that our users see on Astra. So it's come a long way. And while we want this to be open and modular, there's obviously certain software components that aren't that, and that we need to have a solution that you're actually able to adapt to those and leverage the value add when and where necessary. So this is obviously, the foundation of this is the hardware itself, where we could hopefully be able to select from several different operating system layers. Right now, again, we're focusing on TOS, but you could imagine that, we could potentially run OpenSUSE, for instance, or some other Linux-based operating system in the near future, and then be able to layer the programming environment on top of that, whether that's directly through native installation, with a container, or even potentially a VM, that then support our entire sort of production application portfolio. And being able to incorporate different, vendor proprietary or open source tools when and where possible and practical. So this is sort of focusing on this packaging solution that we have. Really, we're focused on the open build service or open build server, but being able to take all the RPMs that, say, RHEL or TOS put together and leveraging them when and where necessary to really build this sort of complete software stack. So this doesn't all just sort of pop out of nowhere, and we're not trying to bite off more than we can chew here. So we've sort of have several key milestones for stepping through this gradually rather than face first. It's coming out a little funny, but essentially we're going to focus initially on some basic benchmarking and acceptance tests here. The classics, HPL, HPCG, as well as some micro benchmarks, and just ensuring that we can check the initial boxes for ensuring that the hardware is there, it works, and it works at a scale in which we could potentially rely on. Then moving again towards some of the more interesting aspects of being able to compile and run production applications, mini apps, et cetera, and then being able to optimize them will be the third step. And so we're expecting this ATSI stack to grow and evolve from that. Initially, we've just focused on building the minimum necessary for this first sort of milestone. And that's been, something that's moved along quickly. And when you actually look at this is a pretty small set of software components that are pretty easy to reproduce. So as I mentioned, we've got this open build service and build farm at Sandia. And we've been drawing on Open HPC and the package management system when and where that fits, and being able to also bring in other components that, say, weren't at the right version or weren't available at all on, as part of the Open HPC framework in the same sort of recipe and the same style as Open HPC. The hope here is that we can not only provide a consistent set of software and tools and programming environment for developers to rely on, but also be able to give back a lot of that feedback directly to the Open HPC community without potentially being hindered by improper or inefficient compiles for individual tools, which can sometimes happen. So, like I said, this is installed and running now on our test bed, and have originally focused on some of the initial mini apps, as well as with the compiler tool chain, including Arm as well as the GNU. We focused on 7.2 mostly because this is of key initial focus and something that our developers are already most familiar with, as 7.2 is sort of the focus for the Sierra system as well. So, but again, this is going to expand and grow fairly quickly here as we move to the next milestone. So, that being said, there's more to this software stack than just putting down and a build farm and putting together a base set of components. There's a whole lot more that we'd actually like to do and that we're hoping to tackle in the coming weeks and months here with this machine. And this is a really exciting opportunity, not only because it's an ARM system and it's a first system that we can really start to experiment with, but the prototype nature of this architecture lets us evaluate other interesting technologies as well. So I mentioned before, we can focus on how do we enable machine learning and data analytics workloads that don't typically fit in the HPC or haven't traditionally had to adapt to an HPC environment. And so we've got plans in place and have been doing experimentation with not only Singularity and Docker, but also VMs, specifically with KVM as well. And so it's a very interesting opportunity to explore bringing in sort of non-standard, non-HPC workloads, as well as using these same technologies to deliver the ATSI programming environment back towards the user community when appropriate. Here's a container with our programming environment. Feel free to use it. Build your applications that may then map directly to our to Astra. So there's other obvious R&D areas here, exploring, I would say, non-Lustre-based parallel file systems. There's numerous opportunities. Lustre is definitely our first plan here, and our plan of record. But there's potentially a lot more opportunities for shaking up some of the parallel storage space. There was resilience studies that I think will be really interesting towards the end of the machine, which I think we far too often forget about. So we really have an opportunity here to, on day one, start those studies, start that investigation, so that there's some really interesting research that we're going to see from that, I hope. And as I alluded to earlier, there's various optimizations that we hope and expect to see by looking at HPC resource of this size and scale. And we plan on exploring sort of this whole sort of kernel spectrum, taking a base, RHEL-based or SUSE-based distro, unmodified, comparing it to, say, an HPC optimized kernel where maybe certain features are turned on or off to lower noise, and seeing what effects that may have at scale, or potentially running, non-Linux kernels or lightweight kernels in their entirety. And within this, we obviously can start to look at sort of ARM-specific optimizations as we progress. So I think this is a really interesting opportunity for this machine in particular to start to explore some of the cooler and potentially more valuable, only at scale, sort of opportunities for the OS research space. So to conclude and try and wrap this up, because I'm probably boring you guys all at this point, this Vanguard program really allows us to take some interesting risks to ensure we are able to, leverage a healthy HPC ecosystem for several years to come. We want to see an increase in technology choices and ensure that our production applications are able to run at scale. And ARM, is our and will continue to be our priority in this space, as sort of signified by Astra. With this, we're bringing along the software components, right? We're building the SATC stack, and we're focusing not only on what we need to provide today, but also how we can discover the right tools for doing that in the future. And I think the scale that we're actually looking at is the right scale to be able to drive future R&D efforts and enable future demand of an ARM-based HPC ecosystem. So with that, if anybody's still awake, I can take probably a quick question.
I think we have about 4 minutes to take questions. Cool. And John's going to run around with a mic, so please wait for him. Any hands up questions? Sai, I think you have one question in the back there. No, you didn't really.
I wanted to ask about the Lustre infrastructure. Are you putting the Lustre client on this system and just tapping into existing Lustre file systems, or are you building a new?
Yes. So obviously we need to ensure that the ARM client is going to be ready and working. The Lustre client for ARM is ready. We're seeing that the 212 is sort of the right, nice point there. The release that's due out in October. The pre-builds for that are all, ready and working and working appropriately. We still need to do a lot of experimentation when it comes to the performance of those builds, but step one is just making sure it works. The actual infrastructure for providing, Lustre, the parallel file system itself is x86 based. That shouldn't really matter because, well, the users will never see that. But eventually it would be really nice if we were able to have, say, an ARM-based LNet router solution, and then, as sort of a next step, and then in the future, it'd be nice to have a truly fully ARM system. So, but I think that'll take a little while to develop, and that sort of falls into more the R&D efforts of this project of, seeing if we can, in the future, support an ARM-based, server, Lustre server solution. So I think we'll get there, but step one is, the client, and all signs point to yes for that.
So Andrew, do you mind if I just talk about it from the vendor's perspective here? We would love to have we would love to have spec'd an ARM-based Lustre server solution. There were many discussions about doing that internally, and we just decided not to do that from just a pure risk standpoint because we had to deliver this, and we talking with the customer about actually what they were trying to accomplish at this point. We just didn't want to bite off more than we could chew. So it was a topic of great discussion internally, and a number of us really swallowed hard when we actually proposed a mixed system.
And we'd love to see that, but that's exactly right. If that's a secondary risk that we don't have to take, then it's okay for, again, this prototype system not to totally go full bore there. The key thing is anything that the users will ever see and touch and use is effectively ARM-based, all ARM-based. So login nodes, everything. We definitely didn't want to do cross-compilation or anything like that. That's a whole other situation there. So.
All right, I think that's all the time we have. So let's thank the speaker one more time.
Thanks.
All right, so our next speaker will be Michelle from EPCC. Did I get that right this time? Yeah. I did, thank you. All right, let's see if we can find. Go. All right, let's see if this is miraculously. No, okay, that's not a functional
Yes, so thanks very much for the invitation. Yes, as just mentioned, I definitely do not work for Dirac, even though it says that on your agenda. I very much work for EPCC at the University of Edinburgh. I will be mentioning Dirac later, though. So I'll be presenting the Catalyst UK programme to you very briefly. So the Catalyst UK programme, for those of you that haven't heard of this, it's a collaboration very much driven by HPE with Arm and SUSE, plus 3 UK university, University of Edinburgh being one of them, the other one being University of Bristol, and the third one, Leicester. And the idea is that there'll be 3 ARM-based HPC systems deployed across the UK. Each university will get one of these systems. And installation is, in fact, imminent. The system is not quite being installed today as the previous one, but it is being assembled at the factory as we speak. So hopefully that means we don't have to wait too much longer for it to arrive at our machine room. Once the systems are installed and live, this program will run for 3 years, so this collaboration will be running, hopefully, in a very fruitful way. So in terms of the systems themselves, a lot has been said in the previous talk, but I will still describe a little of what we have, because it's of a slightly more modest scale, but still worthwhile. So there are HP Apollo 70 nodes, and the clusters at each university will be largely identical. There'll be very minor changes, but largely the same, entirely designed, built, and supported by HPE. Each cluster will be 2 racks, so 64 nodes. We have the 32-core CPUs, so that gives us 4,000 cores, 128 gigabyte of DDR per node, and we also have the EDR InfiniBand network. So another picture of hardware. This one time you have the enclosure from the front rather than from the back, but it's the same thing as we've just seen. The aim of the program, so this program was announced in April this year, so a few months ago now, and it has very specific aims. Okay, the first aim is to investigate and showcase the potential of ARM in the UK in particular, among UK academics and UK industry. The second aim is really more a general aim of driving the adoption of supercomputing in the commercial sector and in industry in the UK. The third point is cooperation with industry to make sure we deploy critical workloads in an optimal way and exploit ARM capabilities as well as we can. And then the fourth point, last but not least, is all about training. So making sure that people, once they come onto an ARM system, will be given the correct training and they can productively work with the system. Because if people can't use the system effectively, they'll be put off and they won't be efficient in using the machines. So how are we going to go about this? We have a distributed deployment of systems, 3 different universities in 3 very different places in the UK. Bristol is a long way from Edinburgh. But the idea is that we're going to be highly collaborative. So we're going to share results, we're going to have joint training sessions, we're going to have joint meetings and share the results of our work. Each site will also take a slightly different approach to what we are planning on doing. And the work that we're doing is pre-agreed with HP and ARM. So it's a fixed work plan. There's some flexibility allowed, but we have agreed in advance what we're going to work on. So I am going to, Simon, who leads the Bristol's Catalyst system, is not here, unfortunately. So I'm just quickly introducing both his plans and the plans for Leicester as well before I go into the details of what we're going to do at EPCC. So Simon McIntosh-Smith, he leads, of course, the GW4 consortium and the Isambard project. So he's got a lot of experience with ARM already. And he's already ported 10 of the most heavily used codes from Archer, the national HPC service, to the Cavium ThunderX2. So the idea for him is, and his team, is to start porting these codes all to the Catalyst and look at the open source tool chains here, Flang, Clang, GNU, and so on, and contribute any of the build scripts, compiled scripts, any of the lessons learned from that porting back. So one of the interesting angles for his team is, of course, that they have a Cray, an ARM-based Cray, and they'll have an ARM-based HPE, and they can do a direct comparison between the two, and that's very much what they're going to focus on, especially looking at InfiniBand versus Aries. They're also going to look at how easy it is to integrate the system with all the other infrastructure they have inside the university, and they're going to look at the underlying libraries as well, so maths libraries, BLAS, and FFT, and so on, FFTW. In terms of the codes they're targeting, as I said, the 10 most heavily used codes on Archer, this sort of varies over time. They're not always the same codes, but these are the ones that they sort of agreed on. So the big chemistry codes like VASP, CASTEB, GROMAC, CP2K, and so on, but some weather codes in there as well, and some engineering codes. The one thing they have largely in common is that they have Fortran codes, which makes life more complicated than if it was just plain C. Everything is already running on the Isambard nodes, apart from Hydra. Hydra is still a work in progress. Additional codes that they want to be looking at, things like OpenFOAM and OpenIFS, more chemistry codes with Casino and LAMPS and so on. But this is very much what they're focusing on, and very much looking at what can we do currently on Isambard, how does it compare with what we're going to be doing on the Catalyst system. The University of Leicester, and here's where Dirac comes in, the University of Leicester is that Catalyst part is led by Mark Wilkinson. He's also project director of Dirac. Dirac provides the HPC resources for all particle physics, astrophysics, QCD, and so on in the UK. So that is very much their angle. Those are the codes and the community they're really interested in. And Leicester hosts the data-intensive part, the data-intensive computing part of Catalyst, of Dirac. And therefore, in Catalyst, that's very much what they're interested in as well. They're wanting to focus on data-intensive workflows. So the codes that the Dirac community use, and they have a very fixed set of codes that they use all the time, those are the codes that they want to be ported to ThunderX2 and then provide guidance to their community. They also want to look at things like the high-performance file systems, so similar to what we've just heard. And they also want to look at MOAB and torque and scheduling. In terms of the actual codes they use, so here's a list. I have to admit, these are not codes that I'm familiar with because I am not working for Dirac. But they're very specific. The top 4 are QCD and n-body simulation and so on and so on. And then the bottom 5 codes, in fact, or 6 codes, are from the wider Leicester research community. So that's data processing from satellites, image processing from electron cryo microscopy, and then looking at engineering codes and so on, image processing, bandwidth limited compressible turbulent flows and so on. So this is it's quite different from what Bristol are planning, but I think there's been a lot of lessons learned that can be shared between the two sites. I'm going to go now into a bit more detail about what we're doing at EPCC, because I know more about this. This part of the Catalyst program is led by Mark Parsons. I coordinate the work, however, so I'll be doing a lot of the day-to-day running of this program. And similar to what Bristol are saying, we're also going to look at heavily used codes on Archer, but also on Cirrus. Cirrus is a tier 2 system. It was an SGI. I guess it's now called an HPE. But again, we're going to use the most heavily, we're going to port the most heavily used codes from Archer over. And this table shows the 30 most heavily used codes last month. For some of those, we don't have to source, they're just user codes, but a lot of these are standard modules on Archer. You just do module list, and you have them all there. And you probably can't read that, but the top one is VASP, GROMAC, CP2K, CASTEB, Quantum Espresso, and so on and so on. So on Archer, these codes have a responsible person. That person ports the code, updates the code. Whenever a user wants something, a plugin or so on, they rebuild it. So the idea is that they do the same on Catalyst. They have got the build scripts for Archer, they have the build script for Cirrus. They're just going to build it again. And hopefully, that way we can populate the machine very quickly with lots and lots of applications. We will build it with different compilers, different libraries. So at the bottom, I also did a modular veil. I did a modular veil on GROMACS. And so we have lots of different versions of GROMACS, some with the Plume plugin, different compilers, and so on. And that's exactly what we want to provide. The idea is that we're not going to optimize performance at first. We just want to build it, just going to get it on there, and that's it. Make as many applications as possible available quickly. One of the key aims of the program is to drive adoption of HPC and make the ARM environment more mature, more stable. So documentation for that is a key part. The people that do all the package supports on Archer, on Cirrus, maintain very clear documentation. They will do the same for this system. Just as they be writing down all their instructions, write their scripts for the national service, they will do the same for this system here. We're documenting all the build process, and then we are feeding this back to the community, the HPC community on GitLab. So it can be used by anybody. We can share it between the other universities. It'll all be open. The expectation is that porting all these codes very quickly, that will unearth issues. Probably not crucial issues for every code, but there'll be issues that we come across. The compilers, the libraries, the network, whatever. We don't know what they are because we haven't done the work, but we're fully expecting there to be problems. We'll document these issues, we'll report them back to whoever is the responsible person for the issue. It may be HPE or ARM or Mellanox or SUSE, whoever. And then we will work with the vendors to resolve these issues as best as we can. And any fixes, as long as they can be in the public domain, will then be published. In terms of performance optimization, so I said that we're going to push as many codes onto the system as we can. Of course, if something is really poor, we will then go in and fix the performance. We're going to pick a handful of codes for in-depth performance optimization. We have performance numbers for Archer and for Cirrus. So we have two systems where we're running exactly the same packages. We have the same people building them and so on and so on. So we'll just build the packages again, and we'll have performance numbers across the machines. And we should be able to very quickly see when there's something significantly wrong. In terms of the codes that we're picking, while I say, well, we're just going to pick the ones that are particularly poor, we do have preferred areas here. Engineering being one of them. So engineering codes, computational chemistry codes are a huge user on our systems. And then weather and ocean modeling are as well. So applications from those domains will be given preferred treatment, or priority, let me say it like that. But it's not an exclusive club. If we come across something that really needs work, but it isn't from those three areas, we're not going to ignore it. Another aim of the project is engagement with industry and commercial users. So our system will be open for people to use from industry. If they get in touch with us and say, we'd like to use your system, that is fine. We can give them an account. Academic and open source codes will come first, so we will not do doors open on day one. We will first want to get some, some of our own codes on there. But once we've got a bunch of codes on there and we're comfortable around the system, we will work with our existing industry contacts to get codes onto the Catalyst system, and this includes ISV codes. We've got good relationships with, the likes of ANSYS and Siemens and so on, and we can just tell them, use the system. We can help them with porting and so on, as much as they want. Small amounts of support will be available, but it'll be largely, they get time and they can play as much as they want. But that's still HPC, largely. and I've mainly talked about HPC, but we're also using more and more using non-HPC applications, lots of deep learning on our systems, data analytics, and so on and so on. So we will look at things like TensorFlow and Caffe and Spark and so on. And we're also looking at modern, in inverted commas, programming languages, so Python and Julia and whatever people want to use. So again, that is sort of, that is the more flexible area. So looking at these topics in general will be something we want to do. We'll have to have a use case in order to look at something like Julia, for instance. We're not just going to spend a lot of time on it if we don't have a use case. But if we do, we will have a look. In terms of in-depth investigations, it's very similar to what was actually said before. The in-depth investigations we're going to do will come slightly further down the line, but they will be informed by the porting exercise. We're not going to just pick a topic because we want to pick it if there isn't really a candidate to address this. So, but things that we're expecting to target are scientific libraries, you know, PETSI, FFTW, and so on. And looking at I/O libraries, looking at communication libraries, looking at things like PGAS, for instance. And other areas of interest are things like data layout, memory layout optimization in codes. See what the impact is of having, you know, your 8 memory channels. And then SVE has already been mentioned as well. So we're going to investigate this as well. In terms of training, this is the 4th point that was mentioned from the aims of the project and the collaboration. We do a lot of training. We run one of the PRACE Advanced Training Centers. We run an MSc in HPC, so we do a lot of this. And the first training course that we have that is open to everybody is on the 3rd and 4th of December. 2 days. The first day will be classroom-based theory, and the second day will bring your own code and port it. It's a PRACE course. It's free for anybody to attend, whether from industry or anybody in the world. All they have to do is turn up. So you have to travel to Edinburgh, stay in Edinburgh, but you can attend the training for free. So there isn't any information on the PRACE website yet about this course, but it should be up soon, and then registration will be open. So if you know anybody who might be interested, send them along. And as a summary, final slide, I'm really excited about this program. I can't wait for the machine to arrive, hopefully soon, fingers crossed. And I do think it will really give the ARM ecosystem a bit of a boost and hopefully make the environment mature and stable. And as a final plug is that we have some PhD positions associated with this. So if you know clever people who want to do PhD in sunny Edinburgh, please speak to me. Questions?
Yep, got in the back there to say. Who actually does have a real question this time?
So I wonder what your appetite is for something like joining something like Open HPC or maybe this ATSI effort. It seems to me that we have every one of these ARM sites all promising to come up with their magic scripts and put them on GitHub. Probably just ignore everybody else's GitHub session, things of those as well. So I guess it would make sense perhaps for us to work together on that. I think you probably have maybe some few requirements that are different, but we should probably think about a consortium around that and then share each other's results.
Yeah, I mean, that sounds great.
So how do those of us in warmer climates pay attention and play from home and follow what you're doing, keep up to date?
Well, there aren't any firm plans for disseminating our results or anything like that at this point in time because we don't have a system yet, so we didn't have to worry about it just yet. But I think we will, so a lot of the work we're doing, we push back to the ARM GitLab. And we will be publishing as much of our results and our work as we can. There'll be lots of training sessions that anybody can come along to, and lots of events, hopefully between the 3 sites, not just in Edinburgh. So maybe further south where it's slightly warmer, in Bristol. So that is the plan. The plan is at least for joint events where everybody comes together and reports what they're doing. So it's not just, I've talked mainly about EPCC because that's where I am at, but there'll hopefully be quite a lot of publicity around this once it's going.
All right, so any other questions from the audience? No, all right, let's thank our speaker one more time. All right, so our next speaker will be from Arm, Brent Gorda, who's over inside. There we go. All right. Again, see if this works. No. All right, so you're just going to have to hit enter forward.
Use the keyboard?
Yeah.
Okay.
That's unfortunately dead.
That's fine. Hello. This talk's going to be a little bit different because it's not about a status of any systems. I'm a recent hire here at Arm, and I hope not to use that as a crutch for very long, but I get to use it now. And what I want to do is to introduce myself, give you a little bit of a flavor for my background and the priorities that I'm bringing into Arm. Hopefully they mesh, but hopefully they're also adaptive with feedback from you folks. I've got perhaps an interesting background in the sense that I was around in the early 1990s when microprocessors started taking over from vector systems. So I was at the Lawrence Livermore lab, and we did a project called the Massively Parallel Computing Initiative. Up there on the left, the attack of the killer micros was the catchphrase at the time. And we were very much not in favor with the vector crowd. Cray was not very happy with us at the early days there. Within 3 or 4 years, I was on Cray's advisory board to work with them on the alpha processor, which is what they selected first for the T3D and T3E. Along the way, in an attempt to convince you that I have done some technical work in the past, despite the suit, I wrote a piece of software that scheduled the first parallel machine at Livermore that we called the Gang Scheduler and published it. So a little bit of the research background. When I left Livermore, I handed that to Mojedi and Danny Abel, who turned that into Slurm and have since spun that out into a company. SCEDMD is the name of that company. I went off and, well, another piece that I did there is I wrote a parallel C preprocessor. It was front end of a compiler that had us experimenting with parallel languages. I did one for Fortran as well. And we used that as one of the 3 input languages for what you now call UPC. So then I went off and actually wrote the first Java compiler or worked on the first Java compiler that Sun Microsystems shipped. So I spun off a company and did a couple other things there. In the 2000s, we invented color. And so I went back to Livermore, and I was in charge of the Blue Gene 2nd, 3rd generation, the P and Q architectures. I led the customer side of that, where I worked a little bit with Eric, but a lot of the guys at IBM leading that project off. Along the way, I had this bright idea that since clusters had really come of age, I went to the SC committee and convinced them to hold an event called the Student Cluster Challenge. It's since been renamed to the Student Cluster Competition. And it's now held in 4 regions in the world. So this is the event that you see at ISC and SC, where there's a bunch of students on the show floor. They build up a cluster and they run some of the same applications that our scientists use every day. So that event really took off. That's one of the things I'm pretty proud about. And these days, specifically in China, there's 300 teams show up virtually to vie to be one of the 50 or so that actually physically show up for the final event in China, and then that top team, 1 or 2, are chosen to come to SC and ISC. The impact of that, it's hard to overstate. There's literally thousands of undergraduate students paying attention to high-performance computing, wiring up InfiniBand networks, looking at how to vectorize code on other architectures, but soon on the ARM architecture, I hope. And I want to encourage you as researchers to go visit that at these various events, because it's really good hunting for talent. If you need a PhD student, for example, all of those kids that show up, and they're not all kids actually, the very first year there was a guy my age there. The rule was no degree. You have to be an undergraduate, no degree from any site. And we turned away someone that had a degree from a Bible school the very first year. Anyway, very good hunting grounds, both for the vendors and for the researchers who are trying to get undergrads to sign up for advanced studies. Probably what folks in the room might recognize the most is I spun up a company called WhamCloud, where I was the CEO and wrestled Lustre back into the HPC community when it looked like it wasn't going to be available to us anymore. So it was a company I started in 2010 and ended up selling that company to Intel, where I spent much of the time between 2012 and now. The last 5 years or so I spent at Intel. Semi-retired a year ago and started advising CEOs of startups in Silicon Valley. Didn't get enough of a bite there to make me feel good about things. And so when ARM came calling and said, we've got an opportunity here to make a disruptive change in high-performance computing, that kind of whet my appetite, and I wanted to come back and see if I can't help ARM succeed in here. So from my point of view, there is building momentum here in the ARM community. My goal is to wrap the business side around that and help that to succeed. That is to help researchers get funding. That is to help sites stand up systems. That is to help the software stack mature to the point where it's on par with other options so that the HPC community can really have architectural choice moving forward. I'm really keen to make that happen because I think the last 10 years or so have been the dry years with respect to opportunity for different choices. I'm particularly smitten by some of the architectures that I see coming out. The Fujitsu thing has me excited and asking questions every other day that they won't answer yet. So I'm hoping to learn something this afternoon from Shinji-san. The other piece of this that I think is particularly exciting is the ARM business model allows HPC community server builders, enterprise class customers to take the base architecture and go do interesting things with it, like Google's done with the TPU, like others are doing and soon to be announced. I'm stoked to be able to help that sort of variety come back to our community. I lived through the 90s. If you go to the website, the Dead Computer Society, I lived through that time when there were the CM5s and all those different architectures around. It was really interesting times. And I think we have an opportunity as a community to bring a bunch of that back. And so I'm here to do my best to try and push in that direction. We just heard about the Catalyst program. You know, I agree with a lot of what I hear on that. I do want to see if I can't get my nose in there and follow it really closely, which was why the question. The Sandia machine and the goals there are straight across the plate with respect to the background that I've got. So I'm very interested in watching how that goes. I have been trying my best to study the environment and working with Darren here, I made him build up this slide for me so that we can talk through each of the components and I can understand where the weaknesses are, where we might be able to solicit help to get things going. This turn of the crank, by the way, is not going to be ARM funding everything themselves. ARM is a player here, but only at the IP level. We don't build silicon or systems. So we have to, as a community, evolve this together to make it work for all of us. And so the software stack is a critical piece of that. And so I will be studying all of the activities to try and get myself on top of where the soft spots are in that software stack. And then from a business side, try to fund the sites that are trying to mature that software stack and make it available to everybody. As a Lustre guy, I am pretty committed to the open source aspects of this and a share-all kind of environment. I think that the little exposure that I've had so far, I think that we're starting to see the growing ecosystem, which I am going to argue builds a virtuous cycle, which is everybody sharing and feeding off one another based on the architectural choices that are made, and feeding that back into the IP architects at ARM, but also the silicon partner architects. I think we can get a little bit of a positive feedback loop going here and really come up with some interesting architectures rolling forward. I'm a big fan of the research activity. As I showed, I've attempted to do research funded by Duk in the back, in my background, and appreciate what can be done on that front. I have been CEO of several startups, each of which I've sold off. I'm a big fan of spinning technology off and giving people the entrepreneurial opportunities that come with that. Having done it successfully myself, I can attest to the rewards and the sense of satisfaction that you get doing something like that. And I'm here to help make that happen. So I want to emphasize your role in the community. This isn't just an ARM thing. Think of this as me trying to help you out in all aspects of that. And gratuitously, I managed to put up a slide. I thought this was old information, but when Jonathan, I think, stood up this morning and said, here's the URLs to the information, I guess it's a little bit new. So I wanted to share that in the slides that I'd done before you put those up. Here's where I think you'll be getting your information from us, if not from me directly. And I just wanted to close by handing you my email address and say, please communicate my way. I'm going to try to come up to speed as fast as I can, but I'm working inside ARM to help you succeed. And so I really want to interact with folks. I am in a warmer climate. I'm on the Pacific coast, so my time zone is generally about 5 a.m. Pacific to 5 p.m. Pacific. Those are sort of the hours I keep. I don't race off to the beach in the middle of the day, believe me. And I really would like to hear from folks. So if there's any questions, I'm getting echoed back and forth here, but if anyone wants to ask questions or come up to me later, I'd love to meet everyone who's interested in interacting with us. And what did I miss, Darren? I own the business end of HPC here. Eric owns the technical end. And among those of us doing this, we're really stoked to be seeing ARM put more resources into this, and look forward to a really good future.
All right. I think we have plenty of time for questions as well. So again, with the first question.
Ask me a Lustre question. I've been doing Lustre for a long while.
No, my question was going to be on the commercial ISV software. So I think that's the bit that gives me the most heartburn on ARM. You know, I'm at a lab which is fully all in on ARM. We've been in on ARM for a long time. But the commercial ISV stuff is an interesting problem. So we keep hearing, you know, not enough market to port to spend the money. So I just wondered what your plans are around, say, the LS diners and MPP diners of the world, because having those kind of codes on a system that's transformative into who can buy the hardware then.
So I have some history with these folks in the sense that I've got the relationships on board. I don't have what ARM has done to date in that aspect. So I don't think I can literally answer the question. Maybe Darren has some info that he could add to it, but I would take that as next time I'm able to present, I will try to have an update for that for you.
We'll have some ASC, hopefully, on some specific month. Sure. Great.
Hi, you talk about ARM in HPC. I'm wondering what is happening for ARM in the server market, in the data center server market. A couple of years ago, we all hearing this is the year that ARM break into, or maybe the next couple of years, but nothing happening. So what is the
I think there's a lot of activity that I sense has not been made public. I think you'll, in the next, let me be conservative and say by next June, that you would see a lot more public activity there. There is quite a bit going on, despite I think it was Qualcomm publicly changing their minds on the server in the US. I think there's a lot going on there, but what I've heard internally is not public information at this point. I think there's reasons to be very bullish on this front. So I think the right response is stay tuned here, and you'll be pleasantly surprised by what's going to happen in the next year. One of my attitudes, by the way, is that HPC makes a really good testing ground for the enterprise. And inasmuch as HPC can really grow into the deep learning space and those sorts of activities, we can be trendsetters for the broader enterprise market, which would give the vendors more reason to come pay attention to us. Anybody else?
All right, let's thank our speaker.
Thank you.
All right, so our next speaker is going to be Giri from, I want to say Cavium, but Marvell. It's going to be a remote speaker, so give me 1 second to set this up.
All right, Gary, you already have it ready, so go ahead.
Yep. Hello. So this is Giri Chukupalli from Marvell and Cavium. Sorry I couldn't be there. Thanks for your time. So here is the outline of quick outline of my talk. So since Marvell is probably relatively new, I'll give a quick overview of what Marvell does, and then I'll talk about the ThunderX2 architecture, and then adoption in the community, and both in cloud and the HPC space, give few benchmarks, and then close the talk with 3 slides on how I think HPC and AI, especially not just AI, but the data center backend workloads are converging. So the cloud and these large-scale data centers are no longer monolithic. Their own workloads are bifurcating, and the backend workloads are aligning with HPC. So I'll give a few slides on that. Okay, so Marvell and Cavium recently acquired Cavium, and both Marvell and Cavium are fabulous silicon companies, have a wide range of products, all the way from tiny microcontrollers that go into disk drives in a relatively large process technologies or older process technologies, to all the way to large dies and ASICs and SoCs. Like the one that I'm going to talk about, the ThunderX2 server processors on the latest process technology, 16 FinFET. Just to give you depth, this slide shows all the various ASICs and SOCs in various verticals. To give an example is the data center. In addition to the server processors or HPC server processors, there are Ethernet switches, Ethernet controllers, and other security adapters that go into the data centers. The Ethernet fabric is, for example, Rocky V2 compliant latest 100 gig Ethernet switches and controllers. In many of the areas, actually, where we participate, we are either number one or number two, and here I gave some examples, and we hope to be there even in server HPC space, even though we're close to negligible right now. Just to give a quick, so we have architectural license. Actually, as a company, we have both architectural license and the licenses for a large number of ARM IP cores in other divisions. But our team has an architectural license from ARM, and we do the microarchitecture, and all the core and the uncore is custom microarchitecture, and that's how that ARM innovates on the ecosystem and the ISA, and we on the ASICs and SOCs. So here is the, you've seen probably this a lot of times. So here is the ThunderX2 server class processor. It's very similar to Xeon. In many cases, it's actually even micro-architected similarly, where there is no need for differentiation. It should look like just a boring server processor, both from the system administrator and the applications or end user perspective. The memory hierarchy, the core pipeline, it's a fully out of order, multi-threaded core. Instead of 2 threads per core, typically in x86 processors, we have 4 hardware threads per core. Fully pipelined. The total, there are up to 32 cores. We can run up to 2.5 gigahertz. We have 8 DDR channels instead of 4 or 6. There are wide range of SKUs. We support both different packaging options, are socketed and BGA-like to for typically embedded customers. There's wide range of SKUs, and there's the list price. The list price of Skylake is sky high. The more internal architecture of the SoC are the way the core tiles are arranged. The on-die fabric is a wide bidirectional ring that can run at the same clock speed as the cores. A set of 8 4-core tiles are on the bidirectional rings connected through a crossbar along with 2 slices of L3, and the east-west node points on the fabric are the 4 DDR channels on one side and 4 DDR channels on the other side, and the north-south node points are for connecting multi-socket nodes on the top and all the other peripherals, IOs, PCIe, kind of south bridge-like on the south side. In addition, SoC has the on-die ARM Cortex M3 microcontroller to manage the whole SoC and provide the information to the BMC and so on. It has all the typical features of a classic server, RAS, power management, DVFS, things like that, turbo. Here is an example of a platform. There's a large number of platforms. I would say on the order of 10 boards are out there, typical from HPC side, HPE, Cray, Bull, Atos. On the data center side, there's large number of ODMs, and OEMs have both boards as well as platforms. There are several open compute or OCP compliant boards, both single socket and multi-socket boards for data centers. Here is the quick example of the already announced end users that have systems, but there is several large number of platforms or systems out there at the end customers that are not open yet, including some in Japan and at various DOE, DOD, and other weather centers, for example. Here is the slide that I gave independent reviewers that have extensive reviews done. You can take a look at on Anand Tech or on the Serve the Home. There's some other quotes from both semi-accurate, kind of a juicy magazine, or on the tech side that picks up leaks and so on. And you probably already saw the presentation on Astra. So as we speak, it's being deployed, and we hope to see that it will be on the top 500 when the next one is announced in November. And this other example is in UK. There will be several reasonable size systems across at the 5 national supercomputer centers and universities. This is also based on HPE. Cray and Bull Atos systems will also be there at different centers. In terms of the ecosystem, you can see from all the way touching the metal at the bottom, firmware and drivers, wide range of drivers are available for various peripherals and hardware in terms of the Ethernet controllers, as well as the various SATA, USB, and other drives, all the way to the applications on the top. The OS, all the major OS systems are there. Red Hat, SUSE, Canonical, even Windows 10 Server runs on ThunderX2. Wide range of tools, including Arm Alinea tools and the other compilers. And then in the application space, you will hear some more standard ISVs that will announce at the supercomputing, in addition to the one shown here. Trying to do our own CAE modeling run on our own systems. For example, the typical tools that we use from Cadence, Synapsys, and Mentor Graphics. And here is an example of wide range of community codes and widely used open source and applications in various domains. Color coding is roughly aligns with different domains in weather, fluid dynamics, chemistry, physics, and so on. Quickly, just a sample of benchmarks, since a lot of the systems are already out there, customers can benchmark themselves. Here it highlights the memory bandwidth differences between Xeon Skylake that has 6 channels and the ThunderX2 that has 8 channels. And similarly, even though Skylake has almost 4x or 3x the number of flops, peak flops, in terms of the conjugate gradient method, which is a sparse benchmark, we have similar performance as the Skylake socket. In the next 3 slides, I show performance. These are actually done by Pasha from ARM. It's a ConnectX-4 connecting 2 ThunderX2 nodes back to back. These 3 slides show the performance of bandwidth, latency, and messaging rate with respect to message size. As the message size increases, for example, in this case, bandwidth reaches to almost to the peak. So on 100 gigabit, this gets like 94, 96 gigabits per second. And here is the latency. Typical, we are slightly worse than Xeon, I believe. So on the order of 1.2, 1.3 microseconds ping pong latency starts with. Similarly, messaging rate. This is ConnectX-4 that gives about 80 million messages per second as peak. And I think ConnectX-5 gives on the order of 120 million messages per second. And this is another one that Simon from Bristol has done. So it's probably already presented by others. So as you can see, the what I want to highlight is that when the flops heavy codes are there, we typically tend to do not as well. When the codes run from, so when code blocks nicely in memory hierarchy and has vectorizable. Definitely Skylake beats us. And then in the cases where it's anyway memory bound, either memory or the memory hierarchy, shared memory bound, we should do well. And then this is the TCO slide. Even in cases where we are not as good in pure performance per dollar, we should be quite competitive. In terms of the roadmap, the current processor is done in 16 nanometer FinFET. We are taping out something next year that's essentially will have more cores. Of course, move to the latest process technology and use the additional silicon real estate and power to continue to improve the all the aspects of a balanced server processor design. And then the other thing I want to say is that the current one is ARM 8.1 ISA compliant, and as ARM continues to innovate in the ISA space, we'll continue to be at the leading edge. So when they go to 8.4, we'll be 8.4 compliant, and of course we'll move on to the implementing the ARM SVE scalable vector extensions to give a lot more flexible way to vectorize the loops and get higher performance. So the 3 slides that I want to talk about is, as I said, that HPC and machine learning are converging. In the last, let's say starting 2012, there is a sudden growth of these AI applications, especially in specific fields. Some of the key fields are where we have seen enormous success is the natural language processing, image processing, voice, video, and so on. But if you see in the last year or two, the improvement in performance is actually petering out. We already know how to recognize dogs, cats, and basic conversion of language. But to reach the next level of true AI-like performance, the researchers are recognizing the monolithic nature of the current algorithms, and there is an explosion of algorithmic space very similar to the things that happened in HPC over the last 25 years, going from compact, dense algorithms with simple kernels operating on dense matrices to a sparse algorithms with a wide range of algorithmic variations, resulting in complex control flow. So my guess is that very similar to HPC, the machine learning algorithms will become sparse and will become highly control flow complex in the long run. So similarly, even though currently the hardware are either custom ASICs or machine learning hardware are focused on dense linear algebra and compact algorithms, in the long run, they have to deal with complex control flow, sparse data structures and algorithms that spans across thousands of processing elements. So I think rapidly HPC and a broader data center backend workloads are converging, and the amazing thing is floating point arithmetic is becoming again center of the computations. So that's all what I have to say. So if you have any questions, feel free to ask.
All right. So as usual with remote presentations, just like last time, go ahead and wait for the microphone, which is coming around with John, and then I will repeat the question through my little microphone, and then we'll
Jonathan?
hear from Gary.
Hi. I would like to ask about energy consumption. I'm sure that the ARM platform will have improved energy consumption or not. Do you have any measurements?
So
So
the question was on
consumption.
Energy consumption.
Oh,
yes.
energy
Oh,
consumption.
energy consumption.
So do you have any numbers that you could
do you have any
share
numbers
or
that you could share
anything else, Gary?
or anything
Yeah.
else, Gary?
So I mean, I know ARM means low power, but there is no free lunch. So when a large number of high performance cores are there with all the other SoC related hardware or silicon, we have 56 lanes of PCIe Gen 3. We have a very high speed interchip coherency links. There is 32 megabytes of L3 cache. So a high performance processor in latest process technology roughly consumes similar amount of power. So we actually have SKUs going all the way from 85 watts at the bottom, running 24 cores at 1.8 gigahertz, to all the way to 190 watts at the top, running 32 cores at 2.5 gigahertz.
All right. Any other questions? Nope. All right. Let's thank our virtual speaker one more time. All right, so I think we have a 30-minute break now through 1600. All right, so I'll see you guys back in here at 4 o'clock. Thanks.